The first video in this series of tasters about real engineering was called The Tripod of Civilization. That tripod stands on engineering, medicine and agriculture. By the way, think about this sometime. Why does an engineer like a tripod so much? And a four-legged table, not so much? Not all engineers design machines with moving parts. Civil engineers don't. Their structures stand still. Electronic engineers, they deal with electrons that only move at quantum scales. But some engineers do. Think of the engines that power our cars, impel our aircraft, generate our electricity. If I asked you about the vital components of such machines, you'd think in terms of shafts and valves and turbine blades and gears and such like. Almost certainly you wouldn't think of one vital component of every one of these machines. Any solid part that slides metal to metal against another solid part will pluck material from the surfaces. This is wear, and it will start to damage the components and eventually the machine. But worse, those particles, if they remain between the surfaces, will act like sand rolling around, and quite soon wear will accelerate away and the machine will soon start failing to operate properly. And there's the expensive oil. Oil is what they need. Oil is the vital component of virtually every machine on the globe. What does it do? Oil reduces the wear of components rubbing together. It keeps them apart, leaves a gap between them, it stops them touching each other. This is the main job of the oil. Lubrication. It can do this because of its thickness. Viscosity is the technical term. Here is some motor oil in a glass. It's viscous. You'll see it runs relatively slowly like this. It takes about 10 seconds to empty this glass of oil. A more accurate version of this is how the viscosity is measured by the oil companies. This is the same amount of water, coloured so that you can see it. That took about 4 seconds to empty the glass. There is a complication. There's always a complication with engineering. The oil gets less viscous, it gets thinner as it gets hotter. Conversely, it's much thicker, viscosity is much higher when it is cold. That means when it's cold, it needs much more oomph to pump it through the engines to the bearings. What does all this tell us about starting a car when it's very cold in the winter? Lots of drivers in winter go out, start their car, then go indoors, finish their breakfast, leaving the car engine ticking over for about 10 minutes. Then they come back out, it's warmed up, and they drive away. Okay. No. Very bad. A cold engine has very thick oil, and at tick over, a very slow oil pump speed. The result is that very little oil gets to the bearings. Bearings are scraped and worn, and the engine life is very much shortened. Try this instead. Start up your engine and run it for about a minute, sitting in the driving seat, at about twice the tick over speed. This way, at least the oil pump we'll be giving the still thick and cold oil a good punch to get it through to the furthest part of the engine. Then, after about a minute, switch it off, lock up the car, go back indoors, finish your breakfast. Then, after about 10 minutes, the engine will have warmed up a bit, mainly by conduction. Then you can get back in, drive off at a reasonable speed. That way, you'll be reducing the wear and you'll have less risk of having your car twocked. Read my blog for more reasons why this is worth doing, and also some other things you can do on cold starts. Oh, by the way, there are 3 different ways that heat travels about. It's convection, conduction and radiation. They're all very important in the world. Read up about them. Oh, what's TWOC? Taking without owner's consent. Right. Thanks for watching. Come back again soon. Bye.